In the last class, we discussed how to generalize the classical probability space to quantum probability space. So let me recall briefly. So suppose we have a omega script f. This is a classical probability space. This is sample space. This is collection of set which are called events, and this is called probability measure. So given a set here, this is p is a function from here to 0, 1. So it's a function which assigns a value between 0 and 1 to this. That will be the probability of that event. Okay. This is supposed to be what are called yes or no questions based on this sample space, based on an experiment, and that is a probability space for that. So to generalize it, we took all those, we replaced it with A and phi, okay, where A is a, maybe not A, pi of A or something. Well, we first generalized it. There are two notation. Okay, we got it A and phi. Okay, let me come to that. So first, maybe I call it pi of A, pi of A, pi of A. Later, we'll just use A, okay, where A is all functions from this omega to C. You just got all these functions. And this is a vector space. Of course, you can add functions and multiply functions. And this has another thing is f star at t. F star is a new function at t is equal to f bar. Point-wise conjugation, which gives the involution. So this is a star algebra. So A star is a star algebra. And phi is a function, is a linear functional from here to C, which satisfies the condition that phi of f is greater than 0 if f is greater than 0. If you have a positive function that is greater than or equal to 0, and phi of 1, the constant function 1 is 1. It is with this property, I mean, we define what is called a state. So we defined a pi from A into M and C. Okay. We are doing this is the actual quantization. Okay. So we we define a pi from A to M and C, where pi of any f. F is going to be, f is a function from omega. Omega is a finite set. Okay, suppose, I mean, you can take infinite sets, you can do the same, the whole thing, but we are considering only finite probability, finite quantum probability space. Okay. So you can take 1 up to n. Then pi of f will be just the diagonal matrix of f of 1 up to f of n. So this is a diagonal matrix in MNC. In this, if you take pi of f star, it's just pi of f star. I mean, pi of f is a matrix. F star is just the conjugation. If you take the star diagonal matrix, the transpose is itself, and the star is exactly the bar. Okay. So it's basically here. This is the conjugation. Here it is the adjoint. Okay. So we got a representation of this A as diagonal matrix on that. So what we have is now this pi of A and this phi. Phi is again the same phi, okay? Same B we can take. And this, this phi is given by, you know how this phi is defined? That is, phi is defined by expectation. Okay? Phi of f is just expectation of f. Okay? For indicator function, that is just the probability. Okay? Phi of f. Or phi of indicator function 1a is expectation of a, 1a, which is just probability of a. Okay, so we get back we'll come to that. Okay, pi AF is what is called a, pi AF, where pi, this is a star algebra, and this is a state. Where we have the following definition. Definition of a state is phi is from any algebra. Any algebra, you can consider this contained in MNC. Okay? From C is a state if phi of any positive matrix greater than 0 for all A greater than 0. Any positive definite matrix. Okay? And phi of the identity matrix. This is the identity matrix. Okay? Which I write it as 1, identity matrix. equal to 1. That's all. It takes positive matrix to positive numbers. It's a positive, it's a scalar valued function. It's a linear. It's linear. Any linear functional from the algebra, any algebra contained in MNC, this has to be an algebra to see is positive. If it takes positive, I mean, I hope you know what is positivity. Okay, positivity is, I mean, if A in MNC, this is definition. The thing is, when we try to do quantum probability, quantum channel, and all those things. Whenever we want to recall some linear algebra, I will recall briefly. Okay? If I do the whole linear algebra, and that will half of the course will be linear algebra. Okay. So if you don't know, then I will go in detail. Is positive definite if xi is greater than or equal to 0 for all xi in H. Okay. There is a H. Okay. H is, of course, here it is just Cn or whatever. Okay. Here it is just Cn. This is equivalent to saying A is equal to B star B for some G. This you can get it from spectral theory. So if it is positive, we usually assume that A is self-adjoint also, which will follow actually. I mean, for a complex vector space, it will follow, but we can assume it's self-adjoint and satisfies this property in the definition. So it is self-adjoint, though there is a spectral theorem, which I will state in a few minutes. But as you know, then, I mean, it's clear. So by spectral theorem, you have a projection and you have lambda eigenvalues. Since it is a self-adjoint and it is positive, it will be the eigenvalues has to be positive. Okay. Now, so you can have, so it's clear that I mean, you can take the square root, B equal to square root of A itself. The square root of all those lambdas will give you B. So it will look like that. So this is equivalent to saying phi of B star B is greater than 0 for any B. That's what it is equivalent to that. Okay. So this is what a quantum probability space. We have defined that this is just any A which is a subalgebra of M and C, and you have a state phi is a quantum probability space. So how is it a generalization? I mean, here we have commutativity. Okay. So I mean, this is a fact, which actually, see, here what we have done is we have taken a probability space and constructed a commutative probability space, commutative quantum probability space. Okay. But then here there are diagonal matrices, subset of diagonal matrices. Okay. Or it's diagonal matrices itself. Okay. But on the other hand, if you have any commutative algebra, star algebra, then you can actually, I mean, you can find a common orthonormal basis with respect to which it will be diagonal. You can actually do that. So you can actually get a omega script f, all those things. This can be done even for, I mean, that is what is called Gelfand-Neymark theorem. Even for a infinite dimensional C-star algebra, you can do this. Okay. So we don't need that Gelfand-Neymark theorem. Says that if A phi is commutative, I mean, you have a commutative star algebra and you have a linear functional, then it arises from the omega script f and p. Okay. This is the fact. I don't want to get into that. Okay. But we are interested in the case where you have a omega something and you do this construction, you get this as a diagonal with respect to some orthonormal basis, some Hilbert space, some orthonormal basis. Okay, that's all. It will look like that. It's precisely that. All commutative C-star have commutative quantum probability spaces or classical probability space. That's what this says. So to have something quantum, it has to be non-commutative. Okay. So in our case, we will work with M, all matrices. This is our algebra, M and C equal to. Okay. And we have a phi from M and C. Actually, we will not invoke this phi hereafter. Okay, we will get a density matrix, and that's what we will use. So you can forget about all this, whatever the stuff. This is just to tell you how this thing arises as a generalization of classical probability space. Okay, and we will not. I will state the axioms of quantum mechanics, and then we will work with that only. Okay, this is just to mathematically how you get this. Okay? Otherwise, suddenly a density matrix is there. How that is generalized will not be clear. So that's why I'm stating this. Okay. Now we have a phi from M and C to C is a linear functional in a state. Okay. Then there exists a rho in M and C, okay, where it's greater than or equal to 0, okay, and trace of rho equal to 1, and phi is given by with and phi is given by phi of n is given by trace of OA for all A M. Okay. That is how it will look like that. This rho is what is called rho with this property. These two properties, what is called a density matrix. Rho in M and C. I mean, I will explain this. Okay. Rho in M and C such that rho is greater than 0 and trace rho equal to 1 is called a density matrix. Called as a density matrix. Okay. Okay. So why is this true? We will work with M and C, and any such linear function is given by that. That is because of the following. Define. I mean, this is the proof of this, more or less the proof of this. Define the inner product of any T S or T S in M and C. You define the inner product to be trace of T star S. This will be an inner product. If we have a lambda here, that will come as lambda here. Trace is linear, so it will come as lambda bar. If we have any mu here, that will come as mu. So this, and it's clearly linear. So this is a linear function. Okay. So this is an inner product. It is clearly an inner product on M and C. Okay. And notice that this inner product is same as M and C identified with Cn square. This inner product same as M and C identified as C of n square. The reason, you can just compute it, no? Since the following computation. Just compute it. Trace of T star S is equal to summation over I. I consider this as matrix. Okay, as operator. You can write it as operators, or I mean, this is purely defined as operators. Okay, but you can consider with respect to some matrix. So it will be, if you just compute it, then this is just going to be, you have the matrix T of T. Okay, let me have T star of I. No, this is just T star S I. Okay, and which is same as summation over I. T star. Okay, T star is T bar. T star of Ij, any entry is bar of the transpose. Okay, so that will be bar of, this is the matrix entry. So Ji and S of J, yeah, Ji, right? So this is the one. So this is just, now this is just on summation over J. So this is just summation over Ij, T of Ji bar, T of Sji, which is just the inner product in Cn square. Entry wise, you take the bar of this. I mean, if you consider this as a n square tuple, this is just that. Clear, no? So this is just to, and I mean, identify this. If you have the Hilbert, if we consider the norm on that, there is also the, I mean, the n square norm, Euclidean norm. It's the usual L2 Euclidean norm. Okay. Now the Rick's lemma says the following. I hope you know, all of you know this. I don't have to prove it. Any linear functional on C or any inner product space, any H, on H, any Hilbert space, on any Hilbert space H is given by n beta in H, such that any linear function, call it phi, then phi of any xi is equal to this eta. Because of that, so now we come to the proof of that. Oh no. Because of that, this is a linear functional. Now phi is a state free from M and C to C is a state. Okay. Since it is a linear functional, there exists a rho in M and C such that phi of any A is given by trace of rho star. You can take it to be star of that. Okay, I mean doesn't matter. Okay, rho A. Okay, if you want, you can take it that to be rho star, but it will be positive anyway. Rho star equal to rho. Phi of A equal to this. Okay, for all A in M and C. Now, if you take A equal to identity, so this implies trace of rho is 1. Okay. And you have to prove that rho is positive. Okay. And that is clear. Take A to be this vector, this operator. This is a rank 1 projection operator we have defined. Okay. So trace can be evaluated through any orthonormal basis. You can take the usual orthonormal basis or any orthonormal basis. Now you take an orthonormal basis starting with xi and some other vectors. It's always possible. You can, by orthogonalization, you can start with one vector and then so take ONB with xi in that. Okay, with xi as one of the bases. Okay. Then the other thing doesn't matter. So on the other thing, then trace of rho this vector. If you just evaluate this on that, which is equal to summation over the orthonormal basis, which will be just that rho of, rho xi. All the other things, if you take, it will be xi. If you have something, it will be orthogonal to xi, so it will be 0. Okay, check. Eh? Eh. Phi is a linear functional. Where are we assuming phi is linear functional? We are assuming throughout. We have been assuming from the very construction. You have phi is linear. It's always linear. Okay? Our expectation is linear because it's like integration, summation. All those things are linear. Okay, it is in this case it is summation. In general, expectation is an integration, so it's always linear. So this is greater than or equal to 0. So this implies rho is positive. This is what positive definite means by definition. So it is positive. So any, so this is the any, so any linear, any state is actually given by a density matrix. Okay, this is what is called a density matrix. And we will work with M and C, and we will work with by a state or a density matrix. We just mean this. The matrix which is positive definite and trace rho equal to 1. Okay, that's what we will work with. Okay. So this is about M and C. Let's consider M2C, for example. Okay, M2C. So here, I forgot to say something. In the general setup itself, in the general setup, the AP is a quantum probability space. Okay? quantum probability space. So we don't have sample space here. Okay? Because sample space is not possible. I mean, quantum objects or anything does not have the deterministic position. It does not that it has some position. It does. We cannot work like something in this position. It has some probability in this position. It's not like that. It doesn't have a position. If you assume that, that will be a problem. Okay, so it doesn't have a deterministic position at any point, at any point of time. So we don't have sample space. We only have this algebra. So then in a classical probability space, we have sample space and sets, which are called events. What are the events here? Events are projection here. I mean, how do you get back the, if you have a general commutative C-star algebra, how do you get back all the sets there? That is by considering all those elements X in, I mean, consider the events. Events are equal to all those, what is the notation? Let me say X in, this is for the time being, okay? X in A, such that X square equal to X star equal to X. These are self-adjoint idempotents. As matrices self-adjoint, X equal to X star is self-adjoint, and this is X equal to X square is idempotent. These are projections, basically. Okay? I mean, if you have a general algebra, it is idempotents, self-adjoint idempotent. But in MNC, they are just, I mean, if you consider a Hilbert space and everything, these are just projections in that. Okay? And these projections are the events. Projection need not correspond to set, but indicator function satisfies this. The events are sets. Sets can be replaced by indicator function. Those indicator functions, as a function, it satisfies this relation. Okay? Here, the events are all projection. Okay? Events in this A, in this quantum probability space, events are this. And probability of that event is just P of X. I mean, P of X. Probability of this any event, any, maybe I put small e. Okay? That's easy. Okay? Is just probability of this event E is phi of E. Why is this something? It's a number between 0 and 1. Why is it between 0 and 1? E is a projection, so it will be always greater than or equal to 1 and less than greater than or equal to 0 and less than or equal to 1. Okay, so 1 minus E is positive. I mean, E less than or equal to 1 means that 1 minus E is positive. 1 minus E is positive means this phi of 1 minus E is positive because phi is a positive linear function. Okay, and P of 1 is 1. So it is just 1 minus phi of E is positive. So phi of E has to be less than or equal to 1, greater than or equal to 0 because of this relation. Okay? Because E is between 0 and 1, phi is a positive linear functional, P of E is in 0 and 1. So we get a number. Okay? Right? Huh? No, non-commutative, I mean, how will you get a set? You will not get a set. Now, how are we doing in commutative setup? Commutative thing, the point is, if it arises from script F, if you have a set A, okay, then you consider all function and 1A or the 1A for all A. Those are the precisely those functions which satisfies this condition. Okay, when you have a general commutative C-star algebra, commutative algebra, then you can consider these functions. Consider functions which satisfy this. Okay, they are given by the set as a theorem that you do by doing some multiplicative functionals and other thing. I mean, it's called Gelfand process. Okay, but you will not get it. For example, if that is the case, you get something, then E and F, any two and F should commute, right? It will not commute here. Okay? That's abstraction if you want. It is precisely the non-commutativity is abstraction. There. If it is commutative, you will get that. But I haven't gone through the proof of that Gelfand thing. Okay. Okay. So these are what is called event. Now I want to say what is a random variable. Maybe before that I will. So in commutative state, in classical case, in classical probability, a random variable is just a function. It's just a function from omega to r. It's a real valued function. Okay, and it's finite. We are assuming omega to be finite, so we don't need to worry about measurability and all that. In general, it has to be measurable. Okay, you have to talk about sigma algebra and measurable. Okay? So this is a random variable. So when you have a random variable, so here definition, this is a quantum probability space. Okay? A random variable is just a self-adjoint element. A random variable, or it is called, it's better, this is the right word. This is, we will not use this, observable. Observable is the word. Observable is a self-adjoint element of that, self-adjoint operator. If it is contained in that, it is operator. Okay? Operator in A. X equal to X star. Okay? That is why we need it to be a star algebra. If A is there, A star is also there. So an observable is just a random variable. So in quantum probability, in probability, you will consider expectation and expectation. So expectation of X is just summation pi. I mean, if X looks like summation pi that value of xi. I mean, x of I. That will be the expectation, right? So here the expectation is just, that is how it is defined. It is just P of A. For a random variable, it is just P of A. Okay? So this is what is a random variable or a observable in quantum probability. You will come to that why this is the random variable. For example, so why is it self-adjoint? I mean, self-adjoint comes from real variable. But suppose even if you consider complex variables, see the point is this. This is just another blah blah. You need not worry about this if you don't understand. See, in general, if we have a random variable, it's just a function from omega to some r. Okay? Maybe if it is finite, it will take finitely many values, or if it is infinite, it will take it, or it can be continuous, uncountably many, and it can be continuous. I mean, the continuous means omega is continuous, and the function is continuous. Okay? Then we can define some other x inverse, I mean not x inverse, we can define a tx from subsets. I mean, for example, let us say it's a finite subset, okay? For the timing, maybe if that is lambda n, maybe lambda m. Okay? Omega equal to 1 up to n, and m will be smaller than n. Okay? You have a function like that. Then tx is from a subset of this power set of this lambda 1 to lambda m to power set of omega, where this will take any set A to T inverse A. This will give a function. Okay? This will give a function. So if you have any subset here, you will get a subset here. This is the classical case I am talking about. I am talking about the classical case. Okay. In quantum case, quantum probability, so there is no sample space, but we can still consider this. Okay. So if we have a T from P of this, P of some lambda 1 up to lambda n, to projections. Okay. If you have a subset here, you will get a projection here. Okay. That, what does it mean? What does it mean? If you have a subset, you have a projection here for any subset, and that projection will commute and all that. You get a spectral measure. So spectral theorem will say that it gives a self-adjoint operator. So this is how any self-adjoint operator looks like that. Okay. Maybe I mean, you can generally assume that self-adjoint operator is the generally observable. So, but this is the reason. Okay? You have, I mean, if you have a spectral, I will explain that. Whatever we discuss now, I will explain that. So I'm not going to prove spectral theorem. I'm sure you have seen this. So spectral theorem says the following. The theorem, there are many versions, several versions. So this is for a normal operator. Okay. Let T C is normal. That is, it commutes with that joint. That is T star T equal to T T star. It commutes with that joint. Then there exists projections. I equal to this n, I equal to 1 to m or something, m is less than n. Okay. Projection, this is contained in M and C, projection, M and C, such that T look like this, summation lambda I E. Okay. You know this. Of course, we know lambdas are eigenvalues, lambda I are eigenvalues. It satisfies T, xi equal to lambda z, lambda I z for some xi I. And this EI are just projection into kernel of T minus lambda I times identity. This one is the, okay? It's just the kernel of that. It is just the projections of that. And this, I mean, so it is just those spaces which adds up to this. Okay? Now, if you have any lambda, so if you have a singleton lambda I, if you take that map, singleton lambda I will go to the EI. Or if you have some subset where it contains lambda 3, lambda 4, lambda 5, then corresponding to ET, E2, E3, E5, you just take the space generated by that. It's just the addition, E1 plus, because orthogonal projection, you can just add, it will give you a projection. Okay, so it is just the addition of those projections. So that is how for any subset, you get a projection. Okay. This is just to give the how the generalization is. So for us, any observable is just a self-adjoint operator. So now let us consider, let us describe what are called qubits, which are used in quantum computation. So let A equal to M2. Then we want to see what are all the, yeah. Did you watch the last lecture? So better watch. I have explained that. I said that, so for us, any quantum probability space is just a contained in M and C. That's all. A with a state there. A is just a star algebra and that. We constructed this from we can construct a commutative one from classical probability space. Here it need not be commutative. It's an algebra contained in M and C. Algebra over C, of course. It's algebra over C and it's contained in M and C. It's star algebra. Its star is also there. Okay. So if we have A equal to M2C, okay, in this case, what are all the possible states? Number one, and what are all the events? Okay, the events are what? Events are what are called events are the projection, one-dimensional projection. If it is not 0 and 1, it's going to be a one-dimensional projection. You'll just let E be the EB element is an event. By this we mean E equal to E star equal to E square of course. Okay. Then E will look like this, right? I mean, first of all, E is a projection. So, yeah, a projection will have trace equal to half, right? So it will just look like 1 plus z, 1 minus z times half. Okay. 1, okay. That is because trace is 1. Since, I mean, trace will be, I mean, a projection up to, if you diagonalize it, it will look like this. One-dimensional projection. E is a proper projection, and E not equal to 1, E not equal to 0. Okay. If it is a proper projection, then a trace will be equal to 1. I mean, up to diagonalization, it will be some, I mean, it's not with respect to standard orthonormal basis. With respect to some orthonormal basis, it will equal. But trace you can evaluate with respect to any orthonormal basis. So trace of this is 1. So because of that, it will look like this. Okay, for some z in z which is a positive, which is real, z in 1. And it has to be self-adjoint. So it will be x minus iy, x plus iy. This is how it will look. So x, y, z in R, or x, y, z in R3. Okay. So this is how any E will look like. And there is another condition. This is a rank 1 projection. Okay, because we are assuming E is not equal to 1, E is not equal to 0. Okay, so rank 1 projection means determinant of E should be 0. Okay, since E is rank 1, since rank of E equal to 0, sorry, rank of E equal to 1, determinant of E equal to 0. So this implies 1 minus z square minus x square minus y square equal to 0. So this implies 1 minus x square minus y square minus z square equal to 0. So this implies x, y, z is in S1. Given anything in S1, in the sphere, 3-dimensional sphere, we get a projection. Given any projection, we can parameterize by something in the sphere. Okay? Yeah. Exactly. This is precisely that. You can use angle and other thing get this. This is another way. We will come to that also. We will do this also. This is what is called Bloch sphere. This is very important in quantum mechanics. Okay. So we call this as EA. Okay. We call EA. We call this EA, where A is in S1, okay, and half of whatever, 1 plus z, 1 minus z, x minus iy, x plus iy. Okay. Similarly, if rho is a state, I mean, by this we mean the density metric. Okay. Rho in M and C is a state. I may say it's a state. State is a functional, but for us it is only a density metric. Okay. It's a density matrix. The camera is, okay, I'll start writing slightly below. It's a density matrix. So again, rho is positive and trace rho equal to 1. Okay, trace rho equal to 1. So again, rho will look like 1 plus z, 1 minus z, and there is a half here. Okay, and it is positive, so it's self-adjoint in particular, x minus iy, x plus iy. That is a, yeah, I'm sorry, A in S1, x, I mean, A equal to, let's say, A1, A2, A3, then this will be A1 or something. A2 minus I, A3, A2 plus I, A3. Or you take X, Y, Z, doesn't matter, okay? But since I am calling it as EA, I am writing it like that. Okay. Now rho looks like this, okay? Where, I mean, we have used the property that trace is equal to 1. We have half here. And it is self-adjoint, so we have written. We have to use the property that it's positive also. Okay. So determinant of rho is positive, which will imply that x square, the same computation, plus z square is less than or equal to 1. Conversely, for a 2 cross 2 matrix, if the determinant is positive and these entries are positive, Z is less than or equal to 1. So this is positive. These entries are positive, then it is positive. The matrix is for 2. It's not generally true, for 2 cross 2 it is true. So any state is represented by something, the whole, I mean, what is it called? The ball. Okay? So if B1 equal to all those X, Y, Z in R3 such that, I mean, X square plus Y square plus Z square equal to 1, sorry, less than or equal to 1. Okay? You take the closed ball, okay? Then any point, any, we have this row of X, Y, Z as above. Okay? So all events are parameterized by the sphere, the surface of the ball, boundary of the ball, and all events are parameterized by the whole ball, closed ball. And the surface, so it's also EA is also there. EA is also a rho A. But then that is what is called pure state. So I have to say what is a pure state, what is a density. So I haven't defined that. Definition. So state was originally defined as a linear functional, but then we called it as a density matrix. Okay, a rho in MNC, a density matrix or a state. It's also, we also call it a state, is pure if there exists a, like here our Hilbert space is just Cn such that rho is equal to this. It is given by a single vector. This is what is called a pure state. Okay. Why is it called pure? Is through something called extreme point. These are all the extreme points of something, and it's a different theory. Let's accept that this is a pure theory. So this pure state is something arises from a vector. Okay, that is how usually you would have heard it in Hilbert's, I mean, quantum mechanics. A Hilbert space and a vector in Hilbert space. So this gives that pure state. Okay, that's what it means. Okay. Yeah, rho is called mixed state. Mixed state, if not pure. Okay? If that does not exist any vector such that it looks like this. Okay? That is what is called a mixed state. Okay. We will work with mixed state. Usually it is defined through pure state. We will work with mixed state. Okay. So in M2, in 2 cross 2 case, all the pure states are given by the surface. I mean the S1. And all pure state and mixed states are given by any interior point, inner point, okay? Interior point of the ball. So, and events are also given by the surface. Okay. Now I give this as an assignment for whoever taking this course for credit. Others also can do it. So this says the following. Define, let sigma ones are just matrix. Sigma 0 is identity. Okay. And sigma 1 is this flip vector. Okay. Vector is x1, x2. If you apply this, it will become x2, x1. Okay. And sigma 2 is 0, minus I 0. Okay. And sigma 3 equal to 1, 0, 0, minus 1. These are what are called Pauli matrices. Okay. You can define, so you can verify that these are all 4 matrices you have. M2 is a vector space of dimension 4. With respect to Hilbert-Smith inner product, they will form an orthonormal basis. You can verify that. Okay? But that is not the exercise. Exercise is you define sigma of A, where A is in S, not S1, B1, or R3. You can write in A in R3. You have some A1, A equal to A1, A2, A3 in R3. you define sigma of A to be just this. A1 times sigma 1 plus A2 sigma 2 plus A3 sigma. Just add. They are numbers and they are matrices. You can just add. Okay. Okay. So we have got a sigma A. Now we have this is assignment. Just to get used to this. Then you can compute this sigma A, sigma B. They don't compute. Okay, is equal to the inner product between A and B. R3 inner product, or you call it dot product. Okay, this is just R3. Okay, we better write it as inner product of R3. This is the one. I mean, this is the identity matrix times I times sigma of a vector you need A cross B. This is the cross product, right? Vector product. Cross product also, it's called cross product. Okay? Dot product, cross product. Okay? Vector product, which again give you R3 vector, okay, which is orthogonal to both of these things. Okay? So prove the assignment. The assignment is to prove this. Okay? And of course, it is clear that, I mean, by definition, whatever you have done, E of A, also rho of A, by definition, equal to half into 1 plus sigma of A. Okay. Okay. I'm just adding a 1 here, sigma of A. This is E of A. Then trace of rho A equal to half. This is the probability of, this is an event. This is a density matrix. This is a density matrix. This is an event. Okay. For B in S1, A in B1. B1 is the ball. This is a sphere. Okay. For anything anything A in B1, it is a state. For anything B in S1, it is an event. Okay. So that is an event. Rho A acting on EB is just 1 plus the inner product between A and B. Okay, prove this. This is a So all these E1s are what are called qubits. They are given by vectors in C2, and we'll consider qubit again, okay, after defining axioms of quantum mechanics. Okay, so I think I'm done with this preliminary things. Let us state the axioms of quantum mechanics. Okay. Yeah. Rho of A is defined here, no? Any rho of A like this. Rho of XYZ is this. EXYZ is this. Same thing. It's the same thing. Except that where the A comes from. All states are given, all states look like this, are in this form, with XYZ, the tuple coming from ball. All events are in this form, with all this A1, A2, A3 coming from the surface of the sphere. That's all. Okay. Okay. So, well, I will state the axioms of quantum mechanics, and I don't want to give you a detailed review of what happened, how quantum mechanics started. But what is known as, what everybody might be knowing is, in the last century, in the beginning of last century, end of 19th century, no? End of 19th century, it was thought that Newtonian mechanics, Newton's 3 laws, will determine everything. Using that, we can explain. Maybe using Maxwell's wave theory, and there is some statistical mechanics, Boltzmann statistical mechanics. Using these three things, we can explain everything is what we are taught, and there is nothing more to do in physics. That's what they thought. Even wave optics, sound, everything can be explained using this. The heat, radiation, everything. They thought that can be explained using these ideas. So classical mechanics, it was complete. Okay. Then of course came relative theory and quantum mechanics as a shock, because they were not explained to highly speeding objects or bigger things. And also when they looked at quantum theories, when they looked at atomic structure and other things, when they want to describe electrons, movement of electrons and other things, then they thought then that was not enough. The classical theory was not enough. When you look at the black body radiation, for instance, photoelectric effect, where light is like a particle. Earlier, initially Newton said it's a particle, then it was considered as a wave. Then again, Einstein theory says that it has a particle property, and then double slit experiment, all those things. From that, then quantum mechanics is developed. Quantum mechanics is developed by many people: Schrodinger, Heisenberg, Pauli, Dirac, and many others. I will not go into all that. The point is, which I have already said, classical mechanics is what is called deterministic mechanics. Deterministic, in the sense that you can determine, if you know the initial conditions, you know everything. All initial conditions are given to you precisely. Then you can precisely determine how this system will evolve, and at a given point, at the final point, you will be able to derive the conditions, the speed of a particle or anything. You can clearly explain, provided you know precisely what the initial conditions are. But quantum mechanics is indeterministic, or there is intrinsically something random about it. In the sense, you start with some initial condition, you try to explain, you will get different things through different experiments. That's what it says. That's because you can only compute the probabilities. You cannot compute anything else. Okay? So it is that's what being described in this axioms of quantum mechanics and this postulates. So the first axiom of quantum mechanics. The first axiom 1, any quantum system, this is just an axiom, okay? Any quantum system is given or described by a Hilbert space and a state vector, or a density matrix. Usually it's state vector, for us it's density matrix. So a quantum system, it is just a definition. Okay, you don't have to question that. How we determine how it's for a electron, hydrogen atom, all those things will come later. Okay, a quantum system is described by a Hilbert space. For us, it is just a finite dimensional inner product space. Okay, Hilbert space H and a density matrix. No. L of H. Okay. Density matrix or density operator. Okay, you call it density matrix, doesn't matter. Okay, the density operator rho in L of H, which we have defined all these things. This is what the axiom says. Okay. So what does it mean? So this is just the system. See, a system or whatever, you identify something, you want to identify me. You don't identify with my inner organs or something, right? You just look at me and what the face, shape and other thing, using that you look at it. So you know only some properties of me, like my hair or something, and then using that you determine this is this person. Like that, everything is determined like that, not from all the properties. Like that, whatever the property of the quantum object you want to encode and you want to study, depending upon the Hilbert space will change. If you have an electron and you want to consider only the spin of that electron, just a two-dimensional vector space will do. Okay, it is just C2. H will be C2, and it will be given by a matrix, density matrix in M2. Okay, this is if you want to study only, if you want to consider only the spin of electron. Electron may have many properties. Okay, energy level and position, momentum. If you want to consider more properties, the Hilbert space will change. And in fact, it will become infinite when you want to consider position and momentum together. It will be an infinite Hilbert space. Okay, I will come to that later. Even for photon, also the same thing is true. Okay. So how are we? So this just says the Hilbert quantum system is just a Hilbert space and a density matrix. Axiom 2. Okay. So if X is an observable, I mean, this is about measurement. Okay. I will discuss more general measurement bit later. I don't want to bring it now. Okay. So here an observable is measured. So that's what I will observable. An observable is just a, which is a in L of H, which is a self-adjoint operator. Okay. A random variable observable is a random variable, is a self-adjoint operator. Okay, and we have an observable random variable. So and x is equal to x look like this. I mean, let us assume that it is summation lambda I p n 1 to some n. There is no n here, so I'm using n. Summation lambda I e a. Then the probability of x equal to lambda I equal to rho of pi. I'm sorry. I'm in the linear trace of rho pi. Okay. X takes the value, x is an observable. So it takes the value lambda 1 up to lambda n. This is lambda 1, lambda 2, lambda n. This is the set where x is going to take. X is going to take one of these values. These are all values, determined values. But the probability when you measure something, then the probability of measuring x at lambda I, measuring the, I mean, you measure through something, some experiment, you measure. You have an observable, you have a quantum system. An observable is a self-adjoint operator. You measure that observable. Then the probability of getting this lambda I is precisely trace of rho pi. Okay, where pi is the eigen projection corresponding to the lambda, eigenvalue lambda I. Okay, this is what exactly that. So this is the probability which is given. Then there is something called phenomenon collapse. There is something called will collapse once you measure. When you do the experiment and measure it, then there is something called collapse will happen. Okay. So what is after this is just not mathematics. This is a statement. After measurement, sometimes we use measurement. Okay. After measuring, the system will collapse. Once you measure, the whole system will collapse because you have done something. You have measured. So this is the this is what is called the measurement. Not very precisely understood. Not everything is understood about it. Okay. So after measuring, H will collapse to, I mean, the quantum probability space. H and rho is the quantum probability space here. Initially, we had Mn and phi, but here we are having H and rho. Okay, Hilbert space and rho. Okay, will collapse. The system will become, this is the new system after measuring, will collapse to, I mean, pi h rho I, where I will write it here. Okay, where, I mean, okay, I have written pi h, which is our new hi, where rho I equal to E or pi, no, pi rho pi. Okay, this is a positive matrix, but it will not have trace equal to 1. So you have to divide it by trace of pi rho pi, which is just, I mean, you can bring this pi here, it doesn't matter, which I haven't proved. So, okay. So this will have trace 1, and this will be positive. If you have any operator, x positive operator, if you have some a star, this will also be positive. We can check, and we will be using it soon. So that is positive. Okay. So I mean, this happens if the measured value is lambda I. Okay. That is, you are doing an experiment, and you are measuring an observable x. The probability of this x getting this value lambda I is given by this trace rho pi. If you have measured some lambda I, you will get one of these values, lambda 1 up to lambda n. That's what you will get when you do the measurement. Then it will be a classical value. Okay? You measure something, you get a classical value. If that measurement gives the value lambda I, the whole system will collapse to a new Hilbert space, PIH, and your new state will be rho I. That will be just you hit it by the projection, Pi is rho. Okay, you will get a new state, but you will need trace of trace equal to 1, so you divide it by this. Okay? This is a new system now. This is the axiom 2. Okay? This is what is measurement. Okay, it's clear? Any question? So Hilbert space is just a, I mean, a quantum system is just a Hilbert space, and this is how the probabilities are determined. Probability of an observable is determined. Okay. I mean, any projection which are called events, that's also an observable. That's also a self-adjoint. This is more, I mean, its eigenvalues are 0 and 1. And one, I mean, with 1 it takes, I mean, so eigenvalues are 0 and 1. So the same thing applies there. Okay. 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 Then there is axiom 3. This is about considering two systems together. Okay. HA is one system, HA with rho A, HA B with rho B are two quantum systems. Okay. Then the joint system, the joint or the bipartite system is described by tensor product. Okay. And you know, rho B. OA tensor rho B is an operator. It will be a density operator. It will have trace 1 and all that. You can check. It will be positive and all that. We will talk about tensor product of matrices soon. Okay. This is the axiom 3. Maybe this is axiom 2 and this is axiom 3. Doesn't matter. Okay. So joint system. So this is same in classical probability. Classical probability, if you have one probability space omega 1 script f1 p1, another one omega 2 script f2 p2, then the joint one is the product space, because you want to treat them as independent events, independent probability space. You want to have construct one single probability space where these two behaves like independent probabilities. So you just take the product space, that will work. Okay. If we take the coordinate wise projection, that will give the random variable which are independent. Okay. So you take the product space, but if you take the Hilbert space, that will be the function space. That will be precisely the tensors. Okay. Hilbert space is L2 or something. In general also, if you have the product space, the Hilbert space will be the L2 space, that will be tensor product. We will not have, if you take Hilbert space tensor, that will be the clearly the tensor product. Okay. So the function spaces will be tensor products. Okay. So this is consistent with the classical probability space. This is axiom 3. Then there is axiom 4, which is about the evolution of the system. Okay. I will come to that. Okay. So we need to talk more about tensors, but anyway, let me define what a tensor is. If you have a X in MMC, I think I have earlier said it, MMC, okay. Then X tensor Y, it is an operator. I mean, if you want, it is an operator on xi tensor eta, where xi comes from Cn, eta comes from Cm. It is precisely xi tensor y eta. Okay? It is precisely that. This is one way of considering this. Or you want to consider this a matrix, x tensor y is a matrix in nm of C. Okay. How does it look like? This is just x tensor y. You write it as a matrix like this. So suppose xij is the matrix corresponding to x, ykl is the matrix corresponding to that. Then x tensor y at ij, this is just a matrix of matrices. Okay, is just something looks like this: x ij, x11 y, x12 y, like this, x1n y, whatever. Okay? And similarly, I mean, it is something that like a matrix xij, these are numbers, matrix element of that, and put y here. You will get a matrix of matrix. Okay, n cross n matrix with elements with m cross m matrices y. Okay, now you evaluate all of that, you get a nm cross nm matrix. Okay, that is how it is, just to remain the order. Okay, first you have x1 and then fill with all these y elements, and x2, x11, x12 fill with all elements. This is how the tensor product will look like. Okay. If you do the other way, y first or something, that is something like the other way, tensor mn. Okay, both, even though spaces are same, the order will be, there is a flip involved. So they are not same space as it is. Okay, this is just to remind that. So I will state the axiom 4 and then explain it later. Explain it due course. Axiom 4 is the evolution. What is the spelling? Evolution. U is there? O. Okay. Is this right? Huh? Okay. I thought there is a U somewhere. Okay. Evolution of a quantum system. Quantum system is described by a completely positive map. By a what is called a completely positive, I will explain, map on L of H. Whatever it means. Okay. So this is axiom 4. We have to, I mean, this is just gives the framework for doing quantum mechanics. Okay. So what is a completely positive map? Let us describe that. Let us describe it in the algebraic way, whatever we have been discussing till now, probability space and all that. So you have two quantum probability space. One is the Mn with rho, another mm with another sigma something, or another mm. Okay. Now we have a map from here to here. These are what are called, usually called as super operators. Okay. I mean, operators are operators from Hilbert space. These are operators from Mn, algebra to algebra, matrices to matrices. They are called super operators or something. Okay. Suppose if you have a free from Mn to Mn, or you don't worry about this. Let's consider the phi from here. Phi from states on Cn to states on Cm. Okay. I mean, this will be same as that. That's what I want to say. Okay. States on Cn to states on Cm. Okay. That is, if you have a rho on this, that will go to phi of rho. Okay. So first that has to be a state. Okay. So you have a state here, that has to be a state. So if this has trace 1, phi of rho should have trace 1. And another condition is, if lambda is in 0, 1, okay, then lambda rho plus 1 minus lambda sigma should go to lambda of phi of rho plus 1 minus lambda phi of sigma. The reason is the following. You have a quantum state. That quantum state is in two quantum states with rho and sigma with probability lambda and 1 minus lambda. That is same thing as something described by this new state, lambda rho plus 1 minus lambda rho. Okay, just understand. There is no way to distinguish a quantum state which is with probability lambda is a number between 0 and 1. With this and 1 minus lambda with another state, then that is same as saying that by our theory, that is same as saying that the new density matrix is lambda rho plus 1 minus lambda sigma. It's same as that. Okay. So that has to go to the same thing there. Okay. So because of that, we will, if we have a function from phi from states to states, okay, then this is a convex set. States are convex set. If you have a state rho and sigma, then lambda rho plus 1 minus lambda sigma is also a state. right? That's also a state. Okay? That's clear, no? That's it. It will be positive. It will be all that. It will be. So that should go to another. That should respect the convex linear combination here. Okay. So convex linear combination of this should be. I mean, it is supposed to respect the convex linear combination within the state. Any such functional can be extended to a linear functional on the whole of that. That is clear, just by linearity. Okay? Anything. So this phi extends to M and C. I mean, again, I call it as phi to M and C as linear functional, okay? As linear map. So you have a linear map which takes states to states. Okay. So let us determine what is that. Proposition. Phi is a map from MNC to MNC, linear map. Okay. Then P of a state or a density matrix. Yeah. Density matrix is also a density matrix. Also a density matrix. If and only if P is positive. By positivity, it is positive. Positive. Positive means phi of any. Okay, we have already defined phi of A star A is greater than 0 and trace preserving. Phi is trace preserving. That is phi of, trace of phi of A is trace of E. Okay. Proof is very easy. This way is clear, of course. If it is trace preserving and positive, it takes positive elements to positive elements, then of course a trace is just a positive element with trace 1, and it will be taken to a positive matrix and the trace is preserved, so it will be trace 1. So this way is clear. If it is trace preserving and positive, so only the other way we have to prove. If it takes states to states, then it is it's positive and trace preserving. That's what you want to say. So if we have a row, any that P A is in M and C, okay, and A is greater than or equal to 0, okay, then A divided by 1 by trace A times A is a density matrix, right? Density matrix is just positive and trace equal to 1. Okay? So if we just divide it by the trace, that is a density matrix. I mean, this is just direct, very easy. I'm just. Okay. So this is a density matrix. So phi of 1 by trace A times A is also a density matrix. Is also a density matrix. Okay. So this just means 1 by, it's linear, 1 by trace A of, this just means that trace of phi, 1 by trace A of phi of A is positive, trace of that is 1. And then trace of, you can take the trace A outside. Okay. So phi of trace of phi of A, trace of this divided by 1 by equal to 1. This says that trace of A equal to trace of A, and phi of A is also positive. That's all. Because it's a positive number, trace of positive operator is positive. So this proves. Okay. So any reasonable function which should take, I mean, evolution, what is an evolution of the quantum system? You have a Hilbert space, H with the state, okay? That should go to another Hilbert space with another state. That's what an evolution is, okay? So if it evolves, okay, so then if you have a state, it should go to some state. I mean, forget about it's particularly described by some equation, Schrodinger equation that comes later. Mathematically, when we consider quantum probability space, it's a general space, not just applicable for quantum mechanics. So this is also general. Okay? Generally, if you have a quantum probability space, which is just M and C with a density matrix, then you should get a, after some time, you should get a new probability space, the new density matrix. So that should be described by a linear map from here to there, where it takes states to state, and it should be, so that is equivalent to saying it should be positive and it preserves the trace. But then is that enough? Means it's not enough in quantum mechanics. It is enough in a classical theory. Here, what happens is, if we consider bipartite system, if you combine with another system, which we will do it many times, I mean, most of the time, because we want to use entanglement and other things. So we will combine with another set, another system. Okay. So there also it should take as a combine. So if you have a HA and HB, we will consider HA tensor HB, and any rho A will be extended to here as rho tensor 1 or something. Okay, as extended to here. And if you evolve this system, it will together with this, it will evolve, right? If this evolves to some H, maybe call it HC or something, this evolves to HB tensor H. You are not doing anything HC here. You are only applying here. But then it should take any state here, become a state here. You had a state here. There is a combined state. See, the combined state need not be a tensor product. That is the problem. It could be an entangled state, whatever. Okay. But you are applying a linear functional, you are applying something only here. Okay. If you are applying only here means it will be applied as that tensor 1 here. Okay. That should also take state to state. So that should also same as preserve the trace, and that should also positivity preserving. So that is what is called completely positive. Okay. So let me define that, and then that is what exactly what determines that definition. This is just an algebraic definition. A phi from, you can take any algebra or anything, okay, but we take MMC to MMC, okay, is completely positive or in quantum language, this is what is called a quantum channel. A quantum channel is just a completely positive map. A quantum channel or a completely positive is just a completely positive map. It's completely positive if trace of its trace preserved. That is one condition. Trace preserving is just here. It will preserve when you amplify also. And okay. Okay, let me define n positive and then come. If it is, and it is n positive for all n natural number, okay? For any natural number. I will define what is n positive, okay? So it should be n positive for all n. So this is a simpler definition. Phi from, I change this n to k because n is here. I'm sorry. N is here, so it will be changed to k. Okay. K positive. Mn to mmc. mmc is k positive for k in n if the map phi identity tensor phi acting from identity tensor phi. Okay. This is a map from MKC tensor MNC. Okay. I will explain what is this identity to MKC tensor MMC. Okay. This MNC can become MMC. Then M2 MK tensor MN will become MK tensor MM. So if a state is there, then if you apply this identity tensor phi, you get a new state. Okay. So if a system is evolving through phi, this bipartite system will evolve through identity tensor phi. That should also preserve state to state. Okay, is positive. I mean, we wanted trace preserving, so this will also be trace preserving. P is trace preserving, identity tensor phi is also trace preserving. That's not a problem. So that is this. So what is this identity tensor phi? Where it is just this identity tensor phi. So here the elements are given by A tensor B, where A comes from here, B comes from here. Not all of them. That spans the whole thing, but it's only a finite span. Okay. I mean, you should remember that these kind of things, A tensor B, they are not all the matrices here. A tensor B, and then you have to take the span of that. Okay. So identity tensor B is just A tensor P of B. That's all. And it is then extended linearly, and it's a finite linear, so it will extend. There's no problem. It's not an infinite thing, so infinite operators or something. So infinite operator algebra. It's not an infinite operator algebra. It's only finite matrix algebra. So you can extend it. Okay. So this is what is identity tensor phi, and this should be positive. Right? What is? It takes positive elements to positive elements. This is from here to here. You take a positive element here. A positive element need not look like A tensor B with A positive, B positive. It is in this. This is a matrix of Kn cross Kn matrix. So it could be positive anything. So I will come to that. Well, I am again. So you can't work with A tensor B and verify that it is positive. You have to work like this. This is just the definition. Okay, what it actually means is what I am writing. So this MK tensor Mn, okay, MKC tensor MNC is just MKN. It's a Kn cross matrices like this, right? Or A tensor B, you just write it like that. You write you can write it as a product, matrix product, and write it like that. Okay, not matrix product, the corresponding tensor product. Okay, elementary tensor, and then, but that will generate the whole thing, MKN like that. How this identity tensor phi act on this? Okay, identity tensor phi acting on. So anything here in this is R K cross K matrix with entries coming from MNC, right? Right. This is equal to MK of MNC. That's how we wrote it, right? MK tensor Mn are matrices, K cross K matrices with the entries coming from N cross N matrices. Okay, that is what MK tensor Mn is by definition. That's how we defined it. Okay. So identity tensor phi where you have a AIJ, where AIJ is in MNC. Okay. You can verify that this is exactly equal to P of AIJ. This the ith entry is precisely that. This is what is identity tensor phi. To verify this, if two linear map coincide, if it coincides on a generating set, and a generating sets are this, here it will coincide like that, right? This will be, you have AIJ, some AIJ times B. Okay, if you have phi of B here, it will be identity tensor B mean A tensor phi of B. That is precisely AIJ tensor phi of B. Okay, this, I mean, convince yourself. I'll tell you orally what it means. I'm saying you have MNC to MMC, a map phi. Then you define identity tensor phi from just attaching here MKC, attaching this tensor, amplify it by MKC, and both the places. Now we have apply identity tensor phi from here to here. Okay, it is just identity on this. So this is the definition of identity tensor phi on elementary tensors like this, A tensor B, where it is identity on this, phi on this. Okay, but that is not whole of this. That is just generated by this. On this, it is precise on whole of this. How it will look like? Identity tensor phi of Aij. But anything here is a k cross k matrix with entries coming from MNC. On that, it acts like this. It just acts on those entries as P of Aij. Is it clear? Okay. This is how identity tensor P acts. And the verification of that is you verify on the elementary tensors. Okay. If something linear map is same, this is also a linear map. This is also a linear map. They coincide on elementary tensor, the spanning set. So it has to be same. So that is the reason. So completely positive means you define this map. This has to be positive. This is a positive map. So you cannot work with this elementary tensor. You have to take a general positive thing in this MK tensor MN thing, okay, and then apply, work with this definition and show that it is positive. Okay, so that is the thing. I think we will stop. We will start at precisely at 3:30. I think so. Okay, we'll stop.